In section 3.4, we're going to go back to relations strictly and talk about equivalence relations and something called partitions. So let's define what the equivalence relation stands for. It says here, let S be any set and let tilde be a relation on S. Then this relation tilde is called a equivalence relation provided it satisfies that it's reflexive, symmetric, and transitive. So from back when we talked about relations, a reflexive relation is one in which, in this case, S relates to S for all S. Symmetric, if S relates to T, means T relates to S. And transitive means if S relates to T and T relates to U, then S relates to U. So if we have a relation and we can show that it matches these three conditions, then we have a equivalence relation. And as a consequence of this, we'll have some things like partitions that we can talk about in addition. So for our first example, we're going to think about the geometric properties of similar and congruent, and talk about how these could be seen as equivalence relations. So let's say we have three triangles, triangle 1, and then we have triangle 2, which is just a rotation of the triangle 1, but has the same lengths for each of its sides. And then let's say triangle 3 is basically a smaller version of the two triangles from above. So what we're setting up here is that triangle 1 is congruent to triangle 2, since the lengths of corresponding sides are the same. Also, triangle 1, triangle 2, and triangle 3 are similar. By that I mean that corresponding angles are identical in all the triangles, so they're all similar, but only T1 and T2 are congruent. So what does this mean as a relation? Well, if we think about the property of reflexive, does it apply to the congruency or similarity of triangles? Well, if T1 is a triangle, it's similar to itself, so it makes sense that it would be reflexive since every triangle is similar to itself. And so what about symmetric? So if you have a triangle T1 and triangle T1 is similar to triangle T2, then triangle T2 would be similar to triangle T1 if we can reverse the order here. So it is symmetric and then transitive. If triangle T1 is similar to triangle T2 and triangle T2 is similar to triangle T3, then we can understand that triangle T1 is also similar to triangle T3. So the property of similarity of triangles is reflexive, symmetric, and transitive as a relation. And thus we call it an equivalence relation. And so we see the similar situation for congruence. These two relations of similarity and congruence are equivalence relations. And so as we go along here, we're going to talk about something called a partition. So if we have a set, we partition the set into sets which are disjoint, we say, which don't overlap with each other. So for instance, if I had a set S, I'm illustrating here, and I'm starting to partition it into sets A1, A2, A3, A4, A5, and they're non-overlapping. I'm just kind of dividing up the bigger set into smaller sets. I could divide it into another set, A6, and let's just say I keep on going, and then my very last set is set AN. So I'm partitioning it into N subsets. And so the set S, it can be thought of as being made up of the set A1, union with the set A2, union with the set A3, union with all the way up to the very last set, AN. So all the A sets that I've cut the set S into all together, when put union together, join back together to give us the set S as a whole. I'm not missing any part of the set S, in other words. And also, again, each of these A sets that I've cut up the set S into don't overlap with each other either. So one way of denoting that is AI intersect AJ is equal to the empty set for any two sets where I is not equal to J. So for two different sets in the set of partitions. To summarize, the partitions are a collection of subsets of S. To summarize this, let's say that a partition of S is a collection of subsets AI for I equals 1, 2, all the way up to n, such that the union as I equals 1 to n of A sub I is equal to S, and A sub I and A sub j are disjoint for I not equal to j. In other words, two sets which are different in this collection of subsets. So here's how this connects with the relations and the equivalence relations specifically. We're going to define first off an equivalence relation on a set S, given here again by the letter tilde. We define this bracket S to be the set of all T in S such that S relates to T. This set is called the equivalence class containing S. The equivalence classes on a set partition the set into disjoint subsets, of which the union of all subsets is the set itself. So like we were saying, this is how we consider partitioning of a set, and an equivalence class will be one way of partitioning it. And so the theorem 1 here basically kind of summarizes this. It says that if tilde is a equivalence relation on a non-empty subset S, then the equivalence classes of S is a partition of the set S. And conversely, if you have a partition on a set, then all your subsets are automatically equivalence classes corresponding to some equivalence relation on the set S. So let's consider practically how this is working. Let's look at an example. It's a relation on the natural numbers, cross the natural numbers, defined by m, comma n, the ordered pair, relates to another ordered pair k, comma l, if m plus l equals n plus k. What we want to do is show that this is an equivalence relation and see what we get when we start thinking about the equivalence classes created by it. If we're going to show that this is an equivalence relation, we need to show three things: reflexive, symmetric, and transitive. So let's start off with reflexive. To do that, what I'm going to do is I'm going to start out with m, comma n, and say that those are both natural numbers. It's an ordered pair containing natural numbers. Then we understand that m plus n is equal to itself, m plus n. So we can say then by a relation that m, comma n is related to m, comma n for all m, n in the natural number set. A fairly straightforward thing to say, but it does show that this is reflexive. What about symmetric? Well, if we have here m, comma n related to k, comma l, then by our definition of the relation, that says that m plus n is equal to k plus l. So we can easily reverse this around since it's just a regular equals. So we can say that k plus l is equal to m plus n. And as a result, k L is related to MN. And so that's demonstrating that we can start off with M comma N related to K comma L, and as a result flip it around the other way. And so it's symmetric. And then for transitive, if we start with M comma N related to K comma L and K comma L related to P comma Q, let's say, then by what the definition of our relation says, M plus N is equal to K plus L, and K plus L is equal to P plus Q. But since M and N and P plus Q are both equal to the same thing, so we can say then that M plus N is equal to P plus Q, and also that M comma N is related to P comma Q. That verifies that this is indeed transitive. So we've shown that it has reflexive, symmetric, and transitive properties. Now let's discuss the so-called equivalence classes. For instance, we could talk about the equivalence class for 1, 1. So what that means by the definition of equivalence classes is this is the set of all ordered pairs M comma N, the natural numbers cross the natural numbers, such that 1 comma 1 relates to M comma N. So what that means, if we read what our relation says, to be related to each other, 1 plus 1 has to equal to M plus N. So we're given numbers for two of those variables, and it has to equal to M plus N. And so we have to think about all ordered pairs where the two numbers add up to be the same thing as 1 plus 1, or 2, in other words. Obviously, 1 and 1, 1 comma 1 works. 0 comma 2 works, and 2 comma 0. So those are all the ordered pairs with natural numbers where the two numbers in the ordered pair add up to be 2. That's what the equivalence class stands for in this case. Then let's see, the equivalence class of 0 comma 0. To write it out here again, that's the set of all ordered pairs with natural number components such that 0 comma 0 relates to M comma N. That's the same thing as M comma N in the natural numbers cross the natural numbers such that 0 plus 0 equals M plus N. So what ordered pairs would have numbers that match up with this description? Indeed, there's only one, and that's just 0 comma 0. Only way we could have 0 plus 0 equals 0 plus 0, so nothing else would do here. Again, since we're using natural numbers. Now, if we went off into integers and had negatives in there, we could find some other combinations. Okay, one more just to kind of highlight this. Say 1 comma 2. If you'd like to think about it for a second, go ahead and pause the video and see if you can write out what it would say for the equivalence class here. In this case, let's see, we have all ordered pairs here with natural numbers such that 1 comma 2 is related to M comma N. Or another way of saying that is 1 plus 2 is equal to M plus N. Or 3, in other words. So you just have to find ordered pairs where when you add up the numbers you get 3. Let's see, of course 1 comma 2 fits that description from the beginning. 2 comma 1, 0 comma 3, and 3 comma 0. And so this is another example of a equivalence class for this relation. And as we go along here, notice how all these equivalence classes that I've created don't share anything in common. And they never should, because again, we are partitioning things into disjoint sets. And if we keep going, listing out all the different possibilities, sometimes there are a finite number of equivalence classes, sometimes there are not. But in any case, we are seeing, in this case, the ordered pairs being partitioned off into disjoint subsets. Let's look at another example here. We're going to use the function from the real numbers cross real numbers into the real numbers by f of xy equals x squared plus y squared. We want to show that this can form an equivalence relation, and the equivalence class is created by such a relation. So first off, let's write this function in terms of a relation. So let's say that the function f gives a relation of the ordered pair x comma y relates to z comma w if x squared plus y squared is equal to z squared plus w squared. Now what we want to do is demonstrate that this is an equivalence relation, and then go about looking at the equivalence classes. So first off, is it reflexive? So if we start with an ordered pair x comma y with real number components, then we can tell that for all x comma y, x squared plus y squared is equal to itself x squared plus y squared. So what this means is that x comma y relates to x comma y. So it is reflexive. Symmetric. If we start out with xy relates to zw, does it follow that we can reverse it around? If that's the case, then x squared plus y squared is equal to z squared plus w squared. So we can see that z squared plus w squared is equal to x squared plus y squared. Naturally following from what equals can do. And thus z comma w relates to x comma y. So symmetric. What about transitive? Let's demonstrate how that could be true here. If x comma y relates to z comma w and z comma w relates to u comma v, then by the definition of our relation, x squared plus y squared equals z squared plus w squared, and z squared plus w squared is equal to u squared plus v squared. Thus it's not far to say that x squared plus y squared is equal to u squared plus v squared, and as a result, x comma y relates to u comma v. So we've demonstrated that it's transitive. So it is an equivalence relation, and we should be able to show equivalence classes as a result. So let's go through these here. Let's start out with the equivalence class for the order pair 0, 0. This is equal to the set of all x comma y with real number components such that 0 squared plus 0 squared is equal to x squared plus y squared. Well, just like in our last example, only the ordered pair 0, 0 fits this description. Now if we look at the order or the equivalence class for the ordered pair 1, 1, we're looking at all order pairs x comma y with real numbers such that 1 plus or 1 squared plus 1 squared is equal to x squared plus y squared. That's going to be equal to the set of all x comma y in the real number set, across the real number set, such that x squared plus y squared is equal to 2. So we can list out a lot of ordered pairs here with the numbers that we have for real numbers in this set. But one thing that's helpful to note is that this x squared plus y squared equals 2 is actually the equation of a circle in the xy plane of radius square root 2 centered at the origin. So really that's the set of points that we have here as well. We could list out a few examples, but by and large, if we were to visualize the coordinates, that's what we would be seeing here. Let's look at one more here. Let's say the equivalence class for the ordered pair of 0, 1. That would be all the ordered pairs x, y, such that 0 plus 1, or 0 squared plus 1 squared, is equal to x squared plus y squared. Or another way of writing that is the ordered pairs such that x squared plus y squared is equal to 1. And this is yet again another equation of a circle, and so all the ordered pairs in this equivalence class are going to be on a circle centered at the origin, in this case of radius 1. What we can say now is that it looks like our equivalence classes are constructing sets of points which are falling on the circle centered at the origin with increasing values for the radius. So we can construct infinitely many here, but they're non-overlapping circles just with different radiuses basically.